Welcome to my talk. I thank the organizers for giving me an opportunity to present some of my research. I'm Jay Wadekar. I'm a postdoc at the IAS, and today I'll talk about using machine learning to improve scaling relations in cluster cosmology. And this is work done with the people mentioned here, most of whom are at IAS and Princeton and CCA. And this is the work we published in this paper, and some of it is in preparation. So just to give some background, galaxy clusters have been useful for cosmology. What I mean by galaxy clusters is just objects which contain tens to hundreds of galaxies. They are one of the largest bound objects in the universe. Their abundance as a function of their mass and redshift is a sensitive probe of cosmology. This has been used in recent observations of clusters from SZ and X-ray surveys to determine cosmological parameters like sigma 8 or omega matter. One interesting fun fact is that clusters were one of the first probes to use as an observational probe for dark matter. Fritz Zwicky in 1930s actually from the observations of Coma cluster estimated that there is a lot of unseen mass in the universe, and he called this dunkle materiae. So how do we estimate masses of clusters? We use like individual properties of clusters inferred from observations. For example, in optical surveys, we infer the velocity dispersions of galaxies associated with the cluster. And we know from virial theorem that these have a power law relation with the cluster mass. Similarly, in microwave surveys, we infer a quantity as called the Y, which is the integrated electron pressure. And this corresponds to a thermal energy, and it is correlated with the cluster mass as a power law like this, which can be derived from the virial theorem. So traditionally, people have used a single property of clusters estimated from one particular type of observations for determining cluster masses. But then the question we wanted to ask was, can we use additional properties from different wavelength observations of clusters to then infer the masses more accurately as compared to using this single property by itself? So one other way to state the same thing is that we wanted to see whether there are some other parameters which can be added onto the YCMB, and so it can let us infer the cluster masses better. And the challenge here for traditional manual data analysis techniques is that there could be many parameters which can be which can enter the relation here. These parameters can have like correlations amongst each other. We also don't know what functional form to use to combine these. Should we use power laws or some other nonlinear form? So I think like machine learning tools are useful in such cases because we don't need to specify functional forms. We only need to provide data on these properties and the YCMB, and it will figure out an optimal relation. So let me give a brief overview of some machine learning techniques and place them in context. I think there is a trade-off in properties of machine learning techniques. There are deep neural networks on one side, which work with inputs which are very high dimensional, like high dimensional images, high resolution images, or videos. But then they are very less interpretable, and the results may not generalize outside the training set. There are decision tree approaches in the middle, and there is an approach, I think symbolic regression, which we will also use, which is slightly on the left side, which cannot work with high dimensional inputs, which can work with like, say, things less than 10 dimensions or 5 dimensions, and things less than like 10,000 data points in the training set. But then it provides equations which are readily interpretable and can generalize better than the black box machine learning models that people generally use. So to give a simple 2D example of symbolic regression, here I'm showing a data set which we want to find a functional form that fits it. What symbolic regression does is it tries a brute force approach first, iterating over some functional families. For example, it tries cosine, does not work. A linear function works better. A quadratic works even better. But then it finds like an optimal functional form. like this. So note here that it has come up with this functional form by itself, and it also fits these parameters simultaneously while iterating over the functional forms. So as I mentioned earlier, symbolic regression cannot be used on high dimensional data. So we want to first use other techniques which are fast to cut down the parameter space. So here we try to use random forests, and here are the results. In the top panel is the YM scaling relation, and the mass is determined from it. Here I've removed the power law, so one can see the scatter better. In the middle panel is the masses estimated by training a random forest on the Y and other properties of the cluster, like concentration of gas in the cluster, the stellar mass to gas mass ratio, the NFW concentration of the cluster. And one can see that the scatter is reduced. As in the bottom panel, I've shown the relative reduction in the scatter when including these properties. An important thing to note here is that we found that adding other parameters like the richness of the cluster did not improve upon our prediction. So we narrowed down our search to these parameters. And then the second step was using symbolic regression. So here I'm showing the results that we got from this algorithm. In the top panel again is the YM, the traditional scaling relation, and in the second and the third panel, I'm showing these new relations which we got from symbolic regression. So C gas is again, as I mentioned, is the gas mass in the center as compared to the total gas mass. So once we found these relations and we saw that the scatter was being reduced, we tried to think of like what the physical intuition behind them should be. And so for the second equation, I think why this works is because the central regions of clusters are noisy. And what this equation is doing is it is using 1 minus some constant times the concentration of gas. And when it does this, what it is doing essentially is it is downweighting the central regions of the cluster and upweighting the surrounding edges, which are less noisy. And so I think there is less scatter. For the third relation, I think conversion of gas to stars reduces the Y, which causes like some of this scatter. And using this term M star or M gas corrects for this effect. That's why I think we see better results. One important thing to note here is the CNFW is the concentration which obtained from the mass profile of the cluster, which is not directly observable. But C gas can be probed observationally from X-ray or even SZ surveys. And so I think this equation, the second equation, can be used to estimate cluster masses in real observational scenarios. So one caveat with these equations and this previous study is that they were done on Illustris TNG data, but then TNG only has one particular configuration of baryonic feedback parameters and initial conditions. So do our results hold in a more general setting? And we try to use the camel set of simulations for our study. These are simulations which not only vary cosmological parameters, but also vary baryonic feedback parameters like the AGN strength or the supernova strength of the feedback. They also have different prescriptions for introducing these feedbacks. For example, the Illustris TNG and the SYMBA, as I've shown here, like in the dark matter density, it is similar. For gas density, these different prescriptions give you slightly different results. And for the gas temperature, you can see that these give very different results. So we wanted to see whether these different simulations with different feedbacks can, like how do our results, how well our results can reproduce like this scatter reduction that we were seeing. And we saw that in both these cases, we can find a good reduction in the scatter, like a similar improvement using this function form. Okay, so then we like in the first part, we only try to think about clusters, which are like high mass objects, like 10 to the 14 to 10 to the 15. But then we started also looking into like some of the lower mass objects, like 10 to the 13. And here you can see that the scatter is much higher. But the more important problem is that this relation is biased with respect to the virial theorem relation. And this occurs because for these group scale objects, the gravitational potential well is not very steep. And so baryonic feedback can actually like eject gas from these clusters of groups. So we wanted to see whether we could reduce this effect. So this YM relation can be used even to lower masses. And so we played the same game, like try to see whether you can introduce some additional parameters, complementary information from different surveys to reduce like this deviation. And by tinkering, we found that m star over m gas, this one parameter actually does reduce this relation. So this was like manual tinkering, and then we tried to see whether we could optimize this using symbolic regression. So we started with this and tried to see whether the symbolic regressor can come up with an even better solution, and it did. So it actually like multiplied concentration of stars in the numerator and concentration of gas in the denominator, and essentially this is like m star over m gas in the central region, and you can see that the bias is almost reduced. Okay, so let me jump to a very quick part 3. So in the part 1 and 2, I try to we try to use these machine learning models to like improve the scaling relations. But then we were also like wondering about like can we infer like some of the baryonic feedback parameters from upcoming observations and use like the YM relation. So here I'm showing like, because we had access to the camel suite of simulations with different sets of baryonic feedback parameters, we saw that the YM relation varied quite a lot with different kind of feedback configurations. For example, the supernova speed, if we increase it, actually it moves things closer to the virial theorem prediction. The AGN, on the other hand, moves things as we increase the feedback strength, it moves things away from the virial theorem relation. And I mean, one interesting thing is like this relation YM can be observationally constrained. We can infer the Y from SZ surveys, and we can infer masses from galaxy surveys like the shear survey of DES. Here are some of the observational results on the YM. And these observations will improve in with upcoming surveys. So we wanted to see whether observations like these can actually differentiate between different feedback configurations. So in this plot, I've shown like YM relation in 2 different mass bins on the Y and the X axis. So here, like the different points represent the spread in the YM relation with changing baryonic feedback parameters. And we have also shown some of the forecasts on how tightly this YM relation would be constrained by upcoming surveys. So it will be interesting that it is interesting that upcoming surveys will rule out a lot of these parameter space and give us insights into the baryonic feedback configuration, the true baryonic feedback configuration of the universe. Let me summarize. So I have told you like machine learning tools like symbolic regression can make our life easier in high dimensional parameter spaces and help us find some low scatter relationships existing in these in data sets like the cluster data set that we used. So gas concentration, actually we saw that reduces scatter in the SZ mass estimates. Using stellar to gas mass ratio reduces the deviation from similarity for groups. And we are also on the lookout for other scaling relations where we can apply these techniques. To give some quick, like one slide overview of the things that we are thinking about is in cosmology for making like galaxy mocks, or also for inferring cosmological parameters, we use assumptions that the number of galaxies or baryonic properties of the cluster is a function of only the halo mass. But then there could be secondary dependencies here. which are hard to model because these things are the secondary properties are correlated with the halo mass, and it's hard to determine if there is like a hypersurface lying in the halo property space, which can be used to infer these relations more accurately. So we have thought about that a bit. Two of the important scaling relations in cosmology are the Cepheid period luminosity relation, which is used for inferring the absolute luminosity of the Cepheids, which is then used for measuring the Hubble constant. And also Phillips relation for supernova, which is used in a similar way for inferring the luminosity of supernovae. So it will be interesting to see whether using machine learning tools on all the properties of these Cepheids or supernovae that we can get, can they determine these luminosities more accurately than the scaling relations, and so can we then use them to probe H0 even better. I think these machine learning tools can also be used in galaxy formation for finding or improving upon other relations that have been used earlier. So thanks for listening to my talk, and hope to talk with you more in the conference.